All right, so let's look at hypothesis testing and look at an example of how this works. This is a powerful way to use statistics to test when somebody makes a claim about something. And so in this particular example, somebody is making a claim about a proportion, a percentage. Let me just give you the claim that they're being made. So the claim is this, that the claim is that most people are uncomfortable getting deliveries by drone. Okay, so most people getting drone deliveries. Okay, now let's put that in terms of numbers. Most, there's a, so that's deliveries there at the end. Most is basically real simple, 50%. Okay, so the claim is that most people are uncomfortable. All right, so we might just say 50%. That's how we'll. This is the claim that 50% are uncomfortable. Okay, getting their stuff delivered by drones. Okay, so we might see that claim and we might say, well, whoa, we think that's way too low. We think it's more than 50%. So we actually have what I'm gonna just call real loosely what a counterclaim, and that is it is more than 50%. So the first thing to notice is that this is a claim about a percentage of something, a proportion, right? Remember when we talk about proportions, we're meaning percentages. So that's the claim, okay? Now, before we go on, let's talk about some official language. I've used the terms counterclaim and claim, but the official language is this right here is referred to, the claim is referred to the null as the, let's do it this way. The claim is actually referred to as the null hypothesis, right? Some big fancy term. But it's just the claim that somebody made. And the notation we use is H sub 0. So we'll write it like that. Actually, we'll write it like this because we want it in total symbols here. So we'll write it like this, that H sub 0, that's your null hypothesis, is that P equals 0.50. Okay, that's the claim. On the other hand, the counterclaim, all right, is the alternate hypothesis, what we call the alternate hypothesis. So this is the official language they use there, but it's really just a counterclaim. We're just thinking we're claiming something different, and we're going to use H sub 1, and we think P is actually greater than 0.50. Okay, so very simple. Don't get confused by the notation. Keep it very simple. There's a claim that's made, and then we have a counterclaim. We just want to call BS on their claim. We think it should be more, and so there it is in notation. It's a claim about a proportion. All right. Now, to test this claim, if you think about it, if I wanted to disprove this claim, I would go out and gather my own data. And so that's what we do next. All right? We gather our own data. All right? And so I'm going to put our data in here. So we survey 1,009 people. And from that, we find that P hat, which is our proportion of people that are uncomfortable, is 0.54, right? So we look at that real quick and we say, oh yeah, we got that 54% were uncomfortable. You said that 50% were uncomfortable. We thought that was too low. So it looks like we have disproven your claim, but it's not quite that simple, because that 54% that we get, that 0.54, could just be the result of who we happen to sample. So what we need to do is we can't just compare 54 to 50. What we need to do is we need to standardize these things and find the probability of getting 54 randomly. Okay, so that's what we refer to as the p-value approach. Now you're going to recognize this as something we've been doing, because here's what happens. Um, let's draw a picture of where we're at. And with every hypothesis test, you have a similar picture. You have a normal curve, and right in the middle of the curve is the claimed proportion. They claim that the mean, that p is 50, and that's actually not p. That's they claim that the mean is 50. No, sorry. Let me come back here. I'll just leave it like this. Right? Okay, so that's the claim. Well, we gathered our own sample, and our sample landed up here at 0.54, right? So here's all we need to do. In order for me to really gauge whether 54 is statistically different, significantly different than 50, all I need to do is find this area right here, okay? So you see, this boils down to the same problems we've been doing. Somebody's made a claim, so that gave us the normal curve. We found a sample. We put our sample on their curve, and now we want to find that area. That area is the probability. This is really important. That area is the probability of getting our value, 0.54, or something more extreme. All right? It basically is the probability of getting our result due to chance. So at this point, if I want to find that area, we know what we need to do. We need the z-score, right? So let's find the z-score. And we know our formula for z-scores related to proportions. Square over square root of p times q over n. And that's our z-score formula. And that turns out to be 2.54. Okay? Now, remember, the whole reason we needed that z-score is so that we could find the area, right? And so if we were to look up, we'll look up the area in a second, but the reason we found the z-score is so that we could find the area, right? Now, here's the official language. The official language calls this the test statistic. Okay, so as you go through your process, they ask you, as you go through this hypothesis testing, at some point they're going to say, find the test statistic. Well, in this case, for when we're testing a claim about a proportion, the test statistic is 2.54. It's the z-score. Why do we need the z-score? Because we need to find this area. So even though they're throwing all these terms on you, and you see those in the red here, it boils down to finding areas. Okay, so the test statistic is the z-score, and we need that z-score so that we can find the area. So let's go ahead and find the area. And if I look in my table under 2.54, I'm going to get 0.99, let me make sure, 0.9945. Now remember, that's this area, 0.9945. Okay, but we want this area, so it's going to be 1 minus that. So it's going to be 0.0055. Very, very small, right? Doesn't look like it in the graph, but it is. Okay, so that's the area. Okay, now we need to understand that's the probability of getting the result that we got, the 54, if their claim of 50% is true. And if we look at that, that is less than 1%. It's 0.5% basically, which we know in statistical terms is very, very small. Okay? And represents an unusual or a statistically significant unusual event, right? Because that probability is so small. Now, I want to introduce some new language here. What we just found is an area, right? But here's what they call it. It is called the p-value, the probability value. Okay, so when you see a p-value, when you see them talking about a p-value, it's just the area from your it's the probability of getting the result you did, and in this case, it's the area from your result into the tail. Okay, but it's the p-value. Okay, now at this point, we could, using what we already know, we could say, hey, that is an unusual event. We shouldn't get 54%. because we should only get that, you know, 0.0055 of the time, which is tiny. And so our logic goes like this: that shouldn't happen. So there are two possibilities. Either we just happened to survey a really unique 1,009 people, right? We just happened to get really unlucky or lucky in our surveying, depending on which way you look at it. Or their claim is wrong. Okay? Those are the two possibilities. Well, we know that if we gathered our sample carefully and randomly, then that shouldn't be a problem, right? The sample shouldn't be the problem. So instead, we conclude that their claim must be incorrect. And so we're going to reject it. Okay? Now I'm going to add a little bit more language here, but that's ultimately where we'll be. We'll say, we shouldn't have gotten the 54, therefore we think your claim is incorrect. However, there's a little bit more technical stuff here that it's just doing what we just did, but we've got to use the language here. We talk about the significance level. In all of these problems, you're going to be given a significance level to begin with. And that is simply the cutoff for determining when a p-value is rare or not. So let's say in this case our significant level was 0.05, 5%, right? Basically what we're going to be doing is comparing our p-value to the significance level, okay? In every one of these problems, when you do the p-value method, you're going to compare the p-value to the significance level, whatever the significance level is, okay? And here's how it looks. So in our case, our p-value is 0.0055, and that is significantly less than 0.00 or 0.05, our significance level. Let me write that in this is our p-value, and this is our significance level. Sometimes we just call it alpha, okay? So here's the rule. If your p-value is less than alpha, then you will reach a conclusion. Okay, you always have to come to a conclusion. And it's very simple. If p is less than alpha, your conclusion is this: we will reject the null. Why? Because the probability of getting the result we did, if your claim is correct, is tiny, 0.005. And how tiny is it? Well, it only has to be less than 0.05, our significance level, for us to reject. So our conclusion here is we reject, or in other words, we're calling BS on their claim. We've found evidence that their claim is wrong. The other conclusion we could reach is you might think it would be to accept the null hypothesis, but it is not to accept. We use kind of a funny language. We fail to reject. The reason we use that language is because we can't accept it, but basically we've acknowledged that we haven't found in our study, in our data, enough evidence to reject it. We haven't accepted it, but we just don't have evidence to reject it, so we're failing to reject it. So that is how every test of hypothesis test of a proportion will look when you're using the p-value method. In fact, that's how hypothesis testing will almost always look whenever you're doing it. The only thing that's going to change by and large is the test statistic. You'll use either a different z-score or a t-score if you're testing claims about means.